Welcome. Today we're going to be talking about how you can tackle the RTOS Lab. Before we can get into this lab, we first have to ask one simple question. What is an operating system? An operating system serves two distinct purposes. The first purpose is for it to provide an abstraction layer for your hardware that your programs run on. The second purpose is to provide resource management, say for your programs and how they can use things like memory and disks and other resources. For our purposes though, we're only going to be focusing on one of those aspects in very specific detail, that is, scheduling, or in other words, how much time different tasks or programs get on the CPU. At a high level, you can think of a task as a specific function that a system is required to perform. Say, for example, that you're developing a system to monitor weather data outside. You might, for example, have sensors for atmospheric pressure, for temperature, for humidity, and ideally, you would want a task to measure each one of these sensors to organize your system. So, for example, you could have a task to measure the humidity sensor, the air pressure sensor, the temperature sensor, whatever. Now we have these tasks, but we have one problem. We can only run one at a time because our CPU only has a single core. That's where scheduling comes in. The purpose of scheduling here is to select a task for execution for a specific period of time, so that only one task can run at a time, but we get the illusion that multiple tasks are running on our system. They're just taking up different time slices. So let's consider some of the variables that we might want to have for a task. Like what are the parameters that we would want to assign to specific tasks? So for one thing, we will want each task to potentially have a period. So let's assume for now that each task is repeated over a certain time interval or period. So for example, maybe your weather station would want to take temperature readings once every 10 seconds or so. So therefore its period would be 10 seconds. Another important parameter we have to consider is the execution time of a task. Basically what this means is how much time in a task's period can the task execute for. So what fraction of its period can the task be running on the CPU? Say, for example, our humidity sensor, let's say it has a period with 10 seconds and has an execution time of 1 second. What that means is that in every 10-second interval, that humidity sensor can be sampled only for 1 second, because say perhaps we have other tasks on our system, we would want to limit the amount of time that any particular task can take so it doesn't starve the execution of other tasks. Do note that the execution time of a task is not necessarily all contiguous, and what I mean by this is that it doesn't have to be all lumped together. So for our humidity sensor, for example, we said that it has an execution time of 1 second in a 10-second period. This doesn't mean that the humidity sensor has to execute for 1 second continuously. It can do this in chunks, so it can execute for, say, half a second at the beginning of its period, and half a second in the middle, and then be done for the remainder of its period, or maybe a quarter of a second 4 different times throughout its period. It can be variable. It does not have to be continuous. So NRK basically follows this period execution time model. Each task has a period and a CPU reserve or execution time field associated with it. And there's also a few other fields that are necessary for bookkeeping with the scheduler. Let's take a look at the next wake-up field. What this denotes is how much time in the task's current period is there before we have to wake up the task again and move it back into the ready state. So as an aside, let's talk about task states for a second. So each task can be in a number of states. The two most important ones for our purposes are the ready state and the suspended state. A task in the ready state is available and basically ready to be executed at any time, whereas a task in the suspend state is unavailable to be executed at the current time because it has exhausted its CPU reserve in its current period. So Back to our weather station example. Let's say our humidity sensor with a period of 10 seconds and an execution time of 1 second has just finished its execution time of 1 second. Therefore, at that moment, it would be moved into the suspended state, and when its period comes up again, so when its period resets back to, when its execution time resets back to 1 at the very beginning, then it will be moved back into the ready state. Note that in our scheduler, if a task has a next wake up of 0, that means it can be woken up immediately and will be put back into the ready queue. And that's something we'll touch on when we get into the meat of the scheduler code. The next important field that we're going to look at is the next period. What this means is how much time is left before the task's period begins again. The main utility of this is for keeping track of whether tasks have met their deadlines or not. So in our scheduler code, we're going to take a deep dive into this later, but in our scheduler code, we keep track of how much time has elapsed since the last task swap occurred. And if this time happens to exceed the next period for a task, then we basically say that the task has missed its deadline. And what this means in practicality is basically there was not enough time dedicated to this task on the CPU to meet its to finish its execution time before its period has elapsed. So back to our ever famous weather station example. Let's say that we have 1 second left in the period for our temperature sensor. Let's say that its period is a total of 20 seconds. And let's say we have 1 second left in its period before its period resets again. But let's say its execution time is not 1, but 2 seconds. So there's only 1 second of time that this temperature sensor can possibly run before its period is up. Therefore, we say that its deadline has been missed because there's still 1 second of execution time left that it must run. It's missed its deadline by 1 second in this case. Another field that we're going to be looking at is the suspend flag, and basically what this means is when this is set in our scheduler code, the task will be suspended at the next available opportunity. So you can think of this as signifying that this task will be suspended whenever the scheduler runs again. Note that this is not the same as the task state being suspended. So task state being suspend means that the task actually is suspended. The suspend flag, all that means is that the task will be suspended at the next context switch. So therefore it will be put into the suspend state at the next context switch. One more important field, the CPU remaining, denotes how much CPU time this task has left in its current period before it has to be suspended. So what this means is, for our weather station example, with our temperature sensor of a period of 20 seconds and a CPU reserve of 2 seconds, let's say its CPU remaining is 1 second. So what this means is that this task, this temperature sensor, has been sampled for a total of 1 second. And it has 1 second left to go, 1 second left to be sampled, that is, before we have to put it into the suspend state before we can't run it anymore. So that's the total amount of CPU time this task will have before it has to be suspended again. I will say that this field, CPU remaining, is only updated for the task that has last executed. By this, I mean that this field is only updated when the task has actually run, so when it's actually gotten CPU time. So, for example, if our temperature sensor task has just run and our humidity sensor task is about to be swapped in, only our temperature sensor's CPU remaining would be decremented in this case, because the humidity sensor task hasn't run yet. When that task has run and has finished executing, its own CPU remaining will decrement, but at a later time. The final important field I'm going to get into is task priority, and this is mostly important for when you're doing the rate monotonic scheduling part of this assignment, when you're assigning, say, static priorities to the tasks, you'll use this to denote which task should be favored over the others in the case that multiple tasks are able to run, so are in the ready queue. So like for example, let's say we have a temperature sensor task and a humidity sensor task, and let's say the temperature sensor task has a priority of 1 with the humidity task having a priority of 0. If both were available to run at the same time, then the humidity task, since it has a lower priority number and like a lower absolute number, it will take precedence over the temperature task. So before we get into the details of how we're going to implement this rate monotonic algorithm and later EDF, let's take a look at some of the code that actually does the task switching. So that would be the code that takes whatever task is currently running, saves its state, and brings in a new task. So the way context switching in most OSs occurs is through an interrupt of some kind. Now, you can think of this as basically a function that gets called in response to some event. Now, in NRK, we want context switches to occur periodically, say maybe once every 10 milliseconds or so. So because our microcontroller has a timer on it, this timer, when it expires, can trigger an interrupt, which will then force a context switch to occur, which is what's going on in this pend SV handler function right here. This function or interrupt is triggered whenever the timer on the embed expires so that we can begin a context switch. Now, I'm not going to get into the details of how ARM assembly works, but we'll go through it at a high level, and we're not going to spend much time on this, but we need to get down some basics so that we can understand what's going on at the machine level. So the first thing that happens in this pend SV handler is that we disable interrupts. So like, for example, we would not want to be interrupted in the middle of a context switch because that could corrupt our task state or do some other really bad things and create a lot of race conditions that we don't want. The next thing we do is we take whatever the current value of the stack pointer for the processor is, and we save that into the register R0. The next thing we have to do is save the registers, the general purpose registers, that is. Now, each register, this is a 32-bit platform, so each register is 32 bits or 4 bytes wide, and we have 8 of them. We have R4 to R11, so we have to make 32 bytes of space on the stack, and then we store them simultaneously onto the stack via this STM opcode right here. The last thing we have to do is store that stack pointer that we had previously saved into the task TCB, so the task control block structure that we went over before. Now, NRK has this variable called NRK high-ready TCB, so you can think of this as the task control block structure of the current process that is executing on the system. Now, one important thing to note about NRK high-ready TCB is that in nrk.cpp, it's defined as a pointer, but there's a little bit of a quirk with assembly when you refer to variables, in that in assembly, there's always this implicit added level of indirection. So taking a look at the use of the NRK high-ready TCB in pend SV handler, this is actually a double pointer to the high-ready TCB. What I mean by this is that instead of being just a single pointer, there's actually 2 levels of indirection. So in order to access the stack pointer field, which is the first field in the NRK high-ready TCB, we need to actually dereference twice. So the first time when we do LDR R1 and then R1 in brackets, we dereference it once to get the pointer to the TCB. And then when we store the stack pointer, which was previously in R0, into R1 in brackets, that means that we're storing it into the first field, which is the stack pointer of the TCB. So once we've saved the state of the currently executing task, we can then go to the actual scheduling code, which is in nrkscheduler.cpp. And this is where you as the student are going to be implementing the actual scheduling algorithm to pick the next task that is going to run. So the first thing that we have to do in our scheduling code is we have to determine how much time has elapsed since the last context switch, and then subtract out this value from the CPU remaining of the previously ended task, so the task that had just finished. Now, the amount of time that's elapsed is already given to us. It's in this variable, NRK previous timer val. This is set at the end of our scheduling code below, and basically we can think of this as the amount of time that has elapsed on the system, the amount of, say, timer ticks that have elapsed since the last call to our scheduling code, or the last context switch. So we just subtract out the amount of time that has elapsed from the task that has just ended. But I will note, we only do this for the task that was ended. We don't do this for any other task because CPU remaining represents how much time the task has actually executed on the CPU. Now, if the CPU remaining ever becomes 0, as I said in an earlier part of this video, the task can't run anymore, so we have to suspend it. So we go ahead and set the task state to suspended, and we remove it from the ready queue. Now down below, here's the meat of our scheduling code. So this is most of what you're going to implement for this assignment. There's a little bit below, but this is the bulk of it right here. This for loop over all tasks to this variable, NRK max tasks. So the first thing that we have to do is, if a task is disabled, so if it hasn't been activated yet, then we want to skip it. And as the hint suggests, a task ID of -1 in the task struct denotes whether a task is disabled or not. If it's -1, it is disabled. If it's 0, then it's able to run. The next thing we want to do is reset the task's suspend flag. Now, as I've said before, this is different from the task state being suspended. All the suspend flag means to the OS is that on the next call to the scheduler, we would want to set the task state to suspended. It's not the actual state of the task, it just tells us what we want the state to be on the next call to the scheduler. And since this is the next call to the scheduler, we want all those suspend flags reset back to 0, so we go ahead and do that here. And below that, we do some bookkeeping for the task to make sure that it hasn't missed its deadline. So the first thing that we have to do, we have to update the next wake up variable that we talked about before. Now, there are two situations that can arise here. The first is if, and these both relate to NRK previous timer val, so how much time has elapsed since the scheduler. The first is if next wake up is less than NRK previous timer val. What this means is that the task is ready to be woken up again because more time has elapsed since the last context switch than the amount of time left before the task is ready to be put back into the ready queue again. So if this situation occurs, we would want to, next wake up can never be negative, so we want to set it to 0 in this case. The other case is the more common case, so that's if next wake up is less than or equal to NRK previous timer val. In this case, we would just want to subtract out the time since the call to the scheduler from next wake up. And unlike the CPU remaining that we updated above, we want to do this for all tasks, not just the task that has finished executing currently. The reason for this is because time advances for all the tasks, not just the task that was just finished. So we want to continue to do bookkeeping for all of our tasks because multiple tasks may become ready at once. The second thing that we have to do in this code block is, for code block 2, is we have to update next period. Now, this is kind of similar. There is an additional case that we have to consider here, and that is if next period is less than NRK previous timer val. Now what this means is that the task deadline has been missed. There was not enough time allocated to the task to run to finish before its deadline has finished, before its period has finished. So In this case, we would want to print some sort of an error message. The rest of what you do for that case is up to you. You could set next period back to period if you want, or you could do something else reasonable, but the important thing here is to consider that extra third case. The other two cases are very similar to the ones for code block 1. So if next period is greater than NRK previous timer val, so if there's still time left, then we would just subtract out the elapsed time from next period. Otherwise, for the third case, when next period is equal to previous timer val, we would want to set next period equal to the period of the task. The reason for this is because this means that the amount of time that has been given to the task since the last call to the scheduler exactly coincides with its period being over. So the start of a new period for this task has begun. So we want to set the next period equal to the actual fixed period of the task. If you'd like to see some examples of how these situations arise, take a look at the appendix of a lab document. So below the part where we do the bookkeeping, we're going to be adding tasks back to the ready queue, but only if they're eligible. So tasks are eligible to be added back to this ready queue, so they're able to run again only if they've been previously suspended, so if the task state has been suspended, or if our next wake up is 0, because before in code block 1, we had set next wake up to 0 for a task that is over, or is ready to be run again. So we would want to only add tasks back to the ready queue if our next wake up remains at 0 here. And along with that, there are a few things that we have to do before a task can actually run again. So we have to set 3 fields. So for the CPU remaining field, we want to set that to the fixed CPU reserve of the task, because at the beginning of a task period, its CPU remaining, so the amount of time left for it to execute in its current period, will just be equal to the amount of CPU time it gets for a whole period, which is just its CPU reserve. The task state should be set to ready because the task is ready to run again, it's available to run. And next wake up should be set to next period because the next time the task will be woken up is at the beginning of its next period, which is what next period means. Don't forget to uncomment the line to add the task to the ready queue. And there's one more thing that we have to do in this code block, and that's update the value of this variable called next wake. So what this is that, say for each task there's a next wake up, but we also have to keep track of a separate variable called next wake, which is basically going to be the minimum of all next wake ups of the tasks that we've considered, because we need a way basically to tell the scheduler when to alert itself again, when to run again, and that's what this next wake is for. So below the to-do, just set it to the minimum of all the next wake ups. And there's one more thing that we have to do, and it's maybe 10 or 20 lines below where we set next wake. We have to set next wake potentially one more time, and this is a situation that arises when the CPU remaining of the task that's about to be swapped in happens to be less than next wake. So what this means is that we want to alert the scheduler to run again if the current task finishes before what we had previously considered to be our next wake. So basically what that means is that we want the scheduler to run again as soon as the currently running task has finished its time slice for the current period. So here below this to-do, just set next wake equal to the minimum of the CPU remaining of the task to be swapped in, and the current value of next wake that we computed as the minimum of the next wake ups. Now the main situation where this occurs is if we have a task that finishes, but then there are no more tasks that are eligible to be executed for a little bit. So for example, let's go back to our weather station. Let's say we have our humidity sensor with a period of 10 and an execution time of 1, and a temperature sensor with also a period of 10 and an execution time of 2. Let's say the temperature sensor runs first and then the humidity sensor task runs. So at the conclusion of the temperature sensor task, we want to set next wake up, in this case, not to 8, which is what it would be if we didn't consider the CPU remaining of the humidity task, which is 1. We would want to wake up in 1 second instead of 8 because we need to alert the scheduler that there's no more tasks that are eligible to be run. In this case, the scheduler will run what's called the idle task, which has an ID of 0. It's basically just an empty loop that does nothing until the scheduler runs again, until a new task is ready to be executed again. So that's mostly it for the scheduler code. The one other piece I wanted to show you was back to the context switching assembly code. There's this function called switch that gets called at the end of the NRK scheduler function. And what this does is basically the opposite of pend SV handler. So whereas before we saved the state of the task that was swapped out, we now want to bring the state for the task to be swapped in. We want to put that into the actual processor state, so the registers. So the first thing we have to do is, as before, we have to get access to the stack pointer of the task that's about to be swapped in. So we do this double indirection as I've gone through previously. We want to do that again to get the current stack pointer. We load it into R0, and remember from before, the stack pointer, when we swapped out the previous task, the stack pointer previously pointed to the registers that had been saved there before. So we have to restore those registers first. We do that via the LDM R0 opcode and the R4 to R11. And then after that, we have to add 32 bytes back to the stack pointer so that we can clear the space that we had reserved for those registers. We can clear that back up for use by other things on the stack. So at this point, the stack pointer is where it was when we had first gotten it from the PSP register back up in pend SV handler. It's in the same place at this point. It's in the same state. So we can then go ahead and restore it via the MSR PSP R0 opcode. And after that, we're mostly finished. We re-enable interrupts, and then we return from the interrupt to go back to our tasks. And that's it for my tutorial of the RTOS Lab. I hope this was helpful. If you have any other questions, please feel free to reach out to us on Piazza, and good luck!